a 5-gallon bucket, a pound of ordinary potatoes off the shelf at the IGA, 2 cups of dirt scooped from under the leaves in a patch of woods you can walk to, 2 tablespoons of coarse salt, and about 5 minutes of your Saturday. That is the whole bill of materials for a living factory that sits in the corner of your garage, runs on nothing, plugs into nothing, and doubles its own workforce every 2 days. It builds 6 different plant hormones at the same time while it sits there. And it does what the bottles on the shelf at the farm store are selling for $40 a pint, only better, and for about the price of a bag of potatoes. The chemical companies call those compounds plant growth regulators. The scientists call them phytohormones. And the Korean farmers who worked out how to grow the whole business inside a plastic bucket 60 years ago called them indigenous microorganisms, which is to say, the ones that were already here. Before the end of this, you will have the recipe, exact, and you will understand why it works down at the level of the cell. And you will understand why a $3 billion industry would rather you never learned the name of the Korean man who gave the whole thing away free to the world and never took a dime for it. But none of it makes sense until you understand what is actually going on in that bucket. Because what we are talking about is not fertilizer. Fertilizer is dead. What we are talking about is a living colony of creatures that copy themselves and that make, on their own, the very same hormones the companies build in industrial laboratories at enormous cost. The same hormones that decide whether a seed wakes up, whether a stem stretches, whether a root branches out sideways, whether a fruit fattens or stays small and hard. All of it made by bacteria. All of it made for free. And all of it doubling every 48 hours in a plastic pail in your garage with no power, no motor, no nothing. If you have ever stood in front of that wall at the farm store, looking at little jars with words on them like microbial inoculant and mycorrhizal blend and soil probiotic and biostimulant complex, wondering whether any of it is real, you are about to learn something that changes the whole arithmetic. Because what is in those jars is not modern. It is not a discovery of cutting-edge agricultural biotechnology. The microbes you are paying dearly for were alive in the woods 100 yards from wherever you grew up. They live in the dirt under every healthy tree on this planet. And for thousands of years, farming people on several continents figured out how to collect them, how to multiply them, and how to feed them to a crop, using nothing but rainwater, a source of starch, and patience. The chemical companies worked out how to freeze those same microbes, dry them, seal them in a jar, and charge you $70 for a teaspoonful. A teaspoon of something you could grow yourself, at home, in whatever quantity you cared to make. This is not really a story about bacteria. It is a story about how old farming knowledge gets erased, about how a simple living process becomes a product with a price on it, and about how a billion-dollar business gets built on the backs of organisms any farmer alive could raise in a bucket for the cost of a potato. The modern shape of the story starts in 1965, in a farming village near Suwon, in South Korea. A young farmer named Cho Han-kyu had been watching his neighbors slowly wreck their own ground. Korea in the 60s was in the middle of what the world called the Green Revolution. Synthetic fertilizer coming in from Japan and from the Western chemical houses was being pushed at Korean farmers as the future of everything. And for the first few years, the yields did go up. Then the soil started to give out. The crops got dependent on bigger and bigger doses. The living things in the dirt disappeared. The plants got weak, and the diseases moved in. Farms that had fed the same families for 15 generations suddenly could not bring in a harvest without a shipment of imported chemicals every single season. Cho would not go along with it. Instead of buying what the companies were selling, he turned his attention back to something he had noticed as a boy. Under the fallen leaves in any untouched Korean woods, the ground was alive. It was loose. It was dark. It was shot through with white threads of fungus, and with life you needed a microscope to see. Nobody had ever spread a handful of anything on that woodland floor, and the trees had grown there for centuries anyway, building their own fertility out of nothing but rain, sunlight, fallen leaves, and whatever was working underneath. He spent the next 30 years chasing one question, and it is a question that ought to bother anybody who ever bought a bag of anything. If a woods can feed itself for free, why can't a garden? What he worked out came to be called Korean natural farming, and the heart of it was this. Healthy dirt is not a pile of minerals. Healthy dirt is a living thing run by microbes. Collect those microbes off a healthy woodland floor. Multiply them under conditions you control, and put them back into your own ground. And you can rebuild the same fertility that built the forest in the first place. He called what he collected indigenous microorganisms, and he worked out a 5-stage process to capture them, feed them, and stabilize them. The method spread quietly through Korea across the 70s and 80s. Then in the 90s, his son, Cho Young-sung, took the whole thing and made it simpler, faster, easier to scale up. He called his version Jadam, a Korean word that comes out in English, something like people who resemble nature. The main product of that system is a microbial solution, and where the father's process took 5 stages spread over weeks, the son showed that a similar population of microbes could be raised in one single bucket in 2 or 3 days. And he gave it away. He never patented one step of it. He published the recipe in books and on a free website that is used today by tens of thousands of farmers in Korea, in Africa, across Asia, and in both Americas. Now, here is what makes this thing extraordinary. While Cho Han-kyu was down on his knees in the Korean woods, figuring out how to bottle that biology, a completely separate line of scientific work was running along 10,000 miles away inside a United States Department of Agriculture laboratory in Beltsville, Maryland. Back in 1941, American researchers published a paper about something odd they had seen in pollen. When they pulled compounds out of corn pollen and painted them onto other plant tissue, that tissue grew in a way that did not make sense. The effect repeated every time. Nobody could explain the mechanism. The paper was ignored for the better part of 30 years. Then, in 1970, one of those same researchers, a man named John Mitchell, came back around to the question. This time, his team pulled oily compounds out of rape pollen and put them on bean seedlings, and the growth response was not subtle. The stems shot out. Cell division took off. These compounds were making plants grow in ways the hormones known at the time simply could not account for. They named the new family Brassins, and they published it in Nature, which is the same journal that carried Darwin's most famous work. Then came the part that gets me every time. In 1979, after processing more than 500 pounds of pollen, 500 pounds, just to extract 4 milligrams of the pure compound, the Beltsville team finally got it to crystallize. 4 milligrams. That is about the weight of a grain of sand. They named it brassinolide. And when they got a look at the structure, it turned out to be a steroid. An actual steroid molecule, built along the same lines as the steroid hormones in the bodies of animals. Plants had steroid hormones. They always had. And in 200 years of plant science, nobody had noticed. Brassinosteroids became recognized as the 6th class of plant hormone. We now know they run cell stretching, cell division, photosynthesis, the building of the plant's plumbing, seed germination, fruit set, and resistance to about every kind of stress there is. They work at concentrations of parts per billion, and they are made naturally in every plant on Earth, in the pollen, in the seeds, in the roots, in whatever tissue is young and growing. And here is where the two stories run into each other. The microbes Cho was scooping off the Korean forest floor, the same ones that double every 48 hours in a Jadam bucket, are not generic rot makers. A very large body of peer-reviewed work has documented exactly what they do. They make hormones. The specific families of bacteria that run woodland soil and that bloom in the bucket, the bacillus, the pseudomonas, the azospirillum, and others besides, have been confirmed manufacturing plant hormones as ordinary parts of their day-to-day living. They make indole, 3, acetic acid, which is the main auxin, the hormone that governs root growth. They make cytokinins, which run cell division and the multiplying of shoots. They make gibberellins, which run stem elongation and germination. They make an enzyme that breaks down ethylene and shields plants from stress. And here is the part almost nobody outside specialist microbiology has ever heard. Some of these soil bacteria also turn out compounds with brassinosteroid-like activity. That same steroid family the Americans spent 40 years chasing. The microbes were making it the whole time. They had been making it on every healthy woodland floor on this planet for hundreds of millions of years, before any scientist ever put a name on a single molecule. Let me tell you what that means in practice. When you set up that bucket, you are building a bioreactor, a living reactor. You supply a source of starch, which is the potato. You supply minerals and a stabilizer, which is the salt. You supply the mixed population of workers, which is the woodland dirt. And you supply water and a container, which is the bucket. In the first 24 hours, the oxygen-loving bacteria, mostly the bacillus tribe, start multiplying like a fire in dry hay. By 48 hours, the population has doubled at least once and often several times over, depending on how warm it is. Around 72 hours, the culture shifts toward a closer, more airless state, where lactic acid bacteria and other fermenters start to take over. The potato starch gets converted to simple sugars. The sugars feed the bacteria. The bacteria throw off organic acids that dissolve the minerals out of the salt. And all the way down that cascade, those bacteria are cranking out plant hormones at a rate hundreds of times what they would manage sitting quietly in ordinary dirt. So when you pour the finished liquid on your garden, you are not adding water. You are adding a hormone cocktail. Auxins, cytokinins, gibberellins, brassinosteroid-like compounds, vitamins, organic acids, and a live population of helpers that start colonizing your ground the same afternoon and keep making hormones down there for weeks after. There is no commercial product on this planet that delivers all of that at once, at that concentration, in a live and biologically active form. And the reason there is no such product is not scientific. It is structural. A living bacterial culture cannot be bottled and shipped without constant refrigeration, special packaging, and a shelf life measured in days. The very chemistry that makes this solution so powerful is the same chemistry that makes it impossible to sell in a store. Now you might be wondering whether anybody has actually tested this, whether anybody has put a homemade bucket up against the store-bought jar. They have, and the results matter. Work published across a number of agricultural journals has shown over and over that microbial preparations carrying a diverse population of beneficial bacteria outperform commercial inoculants built on a single isolated strain. One study with a common soil bacterium showed the compounds it released significantly increased tomato plant mass, photosynthesis, and the plant's own levels of gibberellin, auxin, and cytokinin compared against untreated plants. Another documented better root architecture, more chlorophyll in the leaf, and higher yields in tomatoes and potatoes. The body of research on plant growth-promoting bacteria now runs past 10,000 peer-reviewed papers. This is not fringe. This is mainstream, settled microbiology. What gets treated as heresy is the suggestion that a farmer can grow that same community at home for the price of a bucket and a potato. And that suggestion is heresy not because the science contradicts it. The science backs it completely. It is heresy because it threatens the business model. Here is the question the industry hopes you never ask. If these microbes can be grown at home, and if what comes out demonstrably makes the same hormones the products are selling, and if the whole business costs about $2 a bucket and makes enough to feed a whole garden, then why is the global biofertilizer market worth more than $3 billion? And why is it growing 14% a year? 3 things stacked on top of each other. First, standardization and shelf life. A commercial inoculant sold by a big company delivers one named strain at a measured concentration approved by a regulator. Precise, repeatable, the same every time. A bucket of homemade solution holds a wild mixed population that shifts with the woodland dirt you used, the temperature, the season, and your water. Industrial farms cannot run on that kind of variation, but a home gardener can. And a home gardener actually benefits from the diversity in ways a single-strain product cannot touch. The industry built itself on the model that was most controllable and most profitable, and then trained the customer to believe that variety is somehow inferior to standardization. It is not. In the woods, diversity is what holds everything together. Second, the look of complexity. The biofertilizer shelf at the farm store looks like advanced chemistry. Latin names, percentages, microscope photographs, certification seals. It looks like something that took a doctorate to formulate. A bucket of potato water working in the corner of a garage does not look like that. It looks like something a peasant would do. It looks rural. It looks backward. And nobody builds a billion-dollar business on a process that looks rural. But the science under the bucket is not one bit less advanced. It is identical. Same microbes, same hormones, same jobs. What changes is the box, the marketing, and the margin. Third, and this is the one that ought to bother you most, the barrier was language. The Jadam site is in Korean. The original books were written in Korean. The technique spread across Asia and Latin America for decades before there was any decent English translation of a word of it. Search those techniques in Korean or in Spanish or in Portuguese, and you will find tens of thousands of tutorials, videos, demonstrations, whole forums of farmers arguing about it. Search the same techniques in English 10 years ago and you found almost nothing. So while English-speaking gardeners were paying $50 for this biology in a little imported jar, Korean farmers had been growing their own in a bucket for 2 generations. It was never hidden. It was just on the far side of a language wall. And it is not only the microbial solution. The same pattern runs through the whole toolkit. Fermented plant juice, fish amino acid, lactic acid bacteria serum. Most of the regenerative farming kit was worked out and refined in Korea, Japan, India, and the Philippines, decades before Western agriculture would even admit that soil biology mattered. The knowledge was never hidden. It just had not been translated. So, here is the recipe. The 5-minute setup that starts a colony that doubles every 48 hours. The details matter, so pay attention. You need a plastic bucket, around 5 gallons. A plain one. Do not use metal. Metal interferes with the microbes and will rust in the mildly acid conditions of the ferment. You need about 4 gallons of clean water with no chlorine in it. This is not optional. Chlorinated tap water will kill your bacteria before they ever get established. If chlorinated tap is all you have, stand it in an open container in the sun for a day and the chlorine gases off on its own. Rainwater is best of all. Well, water is fine. Filtered works. You need about a pound of ordinary potatoes, 2 or 3 medium ones. Wash them. Do not peel them. Cut them up and boil them in a couple quarts of water for 20 to 30 minutes until they mash easy under a fork. The starch is the fuel the microbes will run on. That cloudy cooking water turns into a starch broth, and it goes in the bucket right along with the potatoes. You need 2 tablespoons of coarse salt or unrefined sea salt. Not fine table salt. Not iodized salt. Coarse or rock salt, the kind that still has its minerals in it. The salt supplies minerals, regulates the osmotic pressure, and at this concentration favors the good microbes over the bad ones. And you need 1 to 2 cups of woodland dirt. This is the critical piece, the heart of the whole thing. Walk into the nearest patch of undisturbed woods you can find. Push the fallen leaves aside and dig down 2 to 4 inches into that dark, crumbly, fungus-threaded dirt underneath. That dirt holds the entire microbial community you are about to multiply. If you cannot get woodland dirt, use the oldest and richest compost you have or worm castings out of an established bin. The setup is the 5-minute part. Take a pair of clean long socks or a couple of squares of cheesecloth. Put the boiled potatoes in one and tie it shut. Put the woodland dirt in the other and tie that shut. Hang both bundles in the bucket so they sit under the water. Throw in the salt, stir the whole thing, and set the bucket somewhere shaded. 60 to 85 degrees is the range you want. Cover it loose with a lid or a cloth to keep the bugs out and slow the evaporation. Do not seal it tight. The ferment makes gas, and a sealed bucket will find a way to let you know about it. That is it. 5 minutes of real work. Now the biology takes over. Within 12 hours, the bacteria are already multiplying. By 24 hours, you will see foam forming on the surface. By 48 hours, that foam is thick and dense and full of bubbles, sometimes visibly working. That foam is the sign the colony has hit its first big explosion. By 72 hours, the thing is fully active and ready to use. In warm weather, it may be done at 48. In cool weather, it may take 4 days. The foam is your gauge. When you see that thick layer sitting on top like bread dough rising, your solution is alive. To use it, dilute 1 part solution to 10 parts water and soak the ground around the base of your plants. Once every 2 or 3 weeks through the season for general soil health, or once a week during active growth if you are trying to bring back ground that has been run into the dirt. And here is the prettiest part of the whole business. 1 finished bucket can start an unlimited number of new buckets. You take half a cup of the finished solution and add it to a new bucket with fresh water, potato, and salt. You skip the woodland dirt entirely after that first one. The colony perpetuates itself. 1 sack of potatoes can produce a whole season's biological feeding off a single original scoop of forest floor. Now let me be honest with you about the limits. Because credibility matters more than excitement. This is no miracle in a pail. It does not replace the need for compost, for organic matter, for mulch, or for mineral correction in ground that has been badly worn out. The microbes need carbon to eat, and soil with no organic matter in it cannot support a strong microbial population no matter how much solution you pour on top of it. The bucket seeds the biology. The compost feeds it. You want both. It is sensitive to cold. Below 60 degrees, the ferment slows way down. Freezing kills the culture outright. The finished solution keeps 2 or 3 weeks at room temperature before the population shifts toward rot and the smell turns on you. You make it, you use it, you make more. There is no shelf life because there is no shelf. Some plants, particularly very young seedlings under 2 weeks old, can be hurt by the undiluted solution because of the acidity and the sheer microbial load. Always dilute. Start weaker than you think on any new planting and watch how the plant answers before you push it. And a word on safety, because it matters. The coarse salt is essential to the recipe, but it has to stay in proportion. Too much salt kills the microbes and will damage your ground if you keep applying it heavy. Stay with the ratio. Always cut it 1 to 10 before it touches a plant. Never iodized table salt. Never a salt substitute. And never pour it on straight. The market numbers finish the picture. The global biofertilizer market ran somewhere around $3.5 billion in recent years and is headed past $8 billion by the end of the decade, growing about 14% a year. The hormone-producing bacteria segment, exactly what we have been talking about, accounts for a big share of that. The margins on freeze-dried bacteria are something to behold. A jar of standardized bacteria retailing for $30 represents pennies of actual production cost. Everything else in that price is packaging, marketing, regulation, distribution, and profit. Meanwhile, a 5-gallon bucket of microbial solution makes 40 gallons of diluted feed for about $2 in materials, carrying not one strain but dozens, working together in ways no single strain product can copy. And it is not the only example. The mycorrhizal fungi that occur free in the dirt of any healthy woods get sold in little packets. Beneficial fungus cultures that grow on rotting wood in any woodlot get extracted, freeze-dried, and bottled. Compost tea anybody can brew in a pail gets sold as a proprietary blend. The whole business model rests on one idea, which is convincing you that biology is too complicated for you to grow yourself. That model has started to crack. As Korean natural farming and the Jadam system and the permaculture movement have spread across continents this last decade, the cracks have widened. The knowledge is finally getting across the language wall. Cho Han-kyu spent 6 decades teaching farmers in more than 30 countries how to make their own inputs. He never patented a single technique. He never took a royalty. He published all of it. His son carries the work on today through Jadam, which runs as a nonprofit teaching network and not as a company. The recipes are free. The lectures are free. The videos are free, and they have been translated into English, Spanish, Portuguese, French, and a growing list besides. The knowledge is being turned loose on the world on purpose, against the whole gravitational pull of a commercial system that would much rather keep it locked behind a brand. Here is what the biofertilizer industry never wanted you to understand. The most powerful soil amendment on this planet is not locked behind a patent or a trademark. It is reproducing right now, this minute, on every healthy woodland floor on every continent. It can be collected with a trowel. It can be multiplied in a bucket. It can be applied for free. Cho saw it in 1965. The Americans at Beltsville identified some of the molecular results in 1970. The microbiologists have spent the last 50 years documenting exactly which bacteria make which hormones and at what concentration. The science is finished. The biology is settled. The only thing standing between you and a garden full of life is one walk into the woods, one stop for a bag of potatoes, and 5 minutes with a bucket. The woodland floor knew. Cho knew. The researchers confirmed the chemistry. Now you know too.